Hi again. So this is basically the Zoom-in session about the Redis streams. Uh, some of you maybe were yesterday at the training day where we basically had a hand-on about streams. Today I'll be talking instead more about the design process that basically shaped the way streams are. And this design process was very long because I wrote a first design document, but it was like not quite good. So instead of implementing anything, I wrote a second version of the design document and wrote the initial stream implementation. And then I wrote 3 design documents for the consumer groups and then implemented the consumer groups. So it was like very slow process, but in order to find, a good API, because it's a complex problem in order to model. It's already the API of consumer groups is quite complex, but without this basic process, it could be even more complex than that. So these are the wrong slides, and I need the new one. This is the keynote. Okay, waiting for the slides to refresh. So basically, in this session, I will try basically to show how the low-level details of the implementations are, what allows Redis to be very, to use little memory, how the consumer groups are represented, and things like that. I'm not sure if the slides is not the right slide, this one. This is from the keynote. I need, please, the slides for the second talk. Yeah, if you want, I can connect my laptop if you don't have them. I have.
Easier, yes.
It is easier. I don't know if they have enough battery, but if there is enough power, that's a possibility. Let's check. Yeah, I have 70%. It's more than enough, I guess. Okay. Oh my God. Okay. Oh. Okay. That's no problem. So you can see, yes. Okay. So basically, the reason in order to add streams was that Redis data structures or PubSub, publish subscribe, is able to model certain problems, but is not able to problem others. For example, take publish subscribe. You can have one publisher and many subscribers to the same channel, and this is basically a model of fan out. However, it's fire and forget. You cannot like publish events that will be saved in Redis. If a client is connected, it gets the event. If the client is not disconnected, there is no way for this client basically to retrieve the history of this kind of events generation. So this is not a good idea. For example, you cannot model easily a chat with that because when the user connects, he wants to see maybe the latest 2 hours of history or something like that, or you may want to also save the chat history in something like Slack in order, for example, then to source a search engine like Redisearch or Elasticsearch or whatever, and so forth. So you can say, I can use lists and with blocking operations in order to implement this kind of messaging. However, with lists are actually queues. So it's a different paradigm. When you fetch an item from a list, there is a single consumer that can fetch a single message. And also the message is removed from the queue in the moment you fetch. So the queue is also not good in order to implement this kind of design like a chat or many problems that are chat-like problems, okay? The other option could be to use a sorted set. And a sorted set basically has no way to consume it. It just is an API and also has a lot of limitations, for example, because it's a completely different idea. You have this item that moves as you move the score. So it's a sort of collection of items associated with a score. Many people tried to abuse the sorted sets in order to model time series or to store a chat. For example, you can use as a score the Unix time, and then as an element what people are writing in a chat. But if they write 2 times like hi, it's the same element, so it's instead an update operation instead of inserting a new operation. So you say, okay, now I'm going to differentiate between the same message, prefixing it with a random string so that each message is different. But we are creating problems after problems. And so basically, Redis had a strong time series data structure, and it had no fan-out way to consume messages. And you can see it as 2 different problems. Initially, we started like that, and thinking, okay, we need something to model time series, and we need a fan-out data structure, like to put reliability on PubSub with the history of messages or something like that. And at some point, I realized that actually they were the same problem, more or less. Two sides of the same problem. So I started to think towards the idea of using a single data structure in order to fix both the problems. And of course, the design ended up being much more complex than that, as it happens often, because as I continued to add more and more things basically to the streams, it was even if every day it was clear that without adding the next step, every client out there would have to re-implement the same thing again and again and again and again. So there was a trade-off between taking things simple and avoiding that the clients would re-implement everything from scratch again and again. So the first step was to implement a good log, because the stream is actually a log, like comma separated value, but in memory, and of course without the limitations of an append-only file, because we are in memory, so we should try to do better compared to a comma separated file. What were the goals? Very compact. You want little memory usage, because of course Redis is in memory. If a stream is extremely good at representing information in memory in a packed way, you can use it for use cases that otherwise will be out of scope, because you say, okay, if I have 5 terabytes, it's a problem. But if the same use case can be modeled, for example, using the 10% of that memory, it's a different problem. And basically, by carefully selecting the right representation for streams, the memory reduction is 90%. 90% of the memory is not used compared to the vanilla representation of streams. Also, it was very important to have range queries, because when streams are used as time series data structure, it's very important to access the history in a very fast way. And also, these range queries, it's very important that are also time related. So for example, If I want, I should be able to say, for example, what are the messages that passed in this chat between 5 a.m. and 6 a.m. of a given exact day. So this was also very important. And this was the side of time series, but also there is also the aspect of consuming the data that arrive as an event sourcing data structure, because you have these events arriving, you log them in a time series data structure, but maybe the same events must be forwarded to other workers that will consume the messages, for example, alerting if there are strange conditions, or aggregating data, or maybe time that, okay, no need. Also, one important thing was I wanted each item inside this stream to have a unique identifier. Back to the example of the comma separated value. Basically, if you don't have a really good way in order to represent a given element inside the file, because you can use, for example, line number, but if I delete one entry, all the offsets will be modified, right? So this is a problem in general in time series. Instead, if each entry has a unique, very clear ID that will never change, a lot of problems become similar to address. So this is the representation which I used. Basically, we have a radix tree, but instead of this radix tree representing a single item per node, I have these macro nodes where there are a lot of items. For example, 80, 100 items for every node. In this way, basically, I have the data structure is accessible in a random way. But because I just pay the price of the radix tree of one node for every 80 items or something like that, the memory usage is like if I just pack everything in a single blob. So it's a very convenient representation. And basically, it's a radix tree, and the items which are packed in these macro nodes are represented by a data structure that's called list pack. Think like BSON. It's a binary serialization format which we designed at Redis Labs, I together with my colleagues, specifically for the Redis use case. But it's like a binary, message pack. There are a bunch. Just we modeled list packs in order to be very efficient with the kind of data that usually people store inside Redis. And then there was a problem about compressing these list packs, these items inside these list packs. What we do basically is to have a header, and this header represents a set of root fields and the number of items and the number of deleted items inside this macro node. Why I have these root fields? Basically, this is the idea. When you add the first entry, you create this header, and you make the root fields the same of the fields of the first entry that you add, because an entry in the stream is like field value is structured like a comma separated file thing. In this way, given that I have a set of root fields, if the next entries have the same fields, I just use a single bit to say, look, this entry has the same fields of the first entry, so I'm going to serialize the values, not the fields again, in order to avoid stating the same fields again and again and again for every entry. And however, in a stream, you are not forced to use the same set of fields for every entry. As you add more data, you can change your mind and say, okay, no, I modified my application. Now I need a new field which I didn't consider at the start. If the fields are no longer the same field compression cannot be used. So basically, the next fields will be like bigger, but then a new node is created after the 80 items, and in the new node, the root fields will be the new format, and so we start compressing again. Instead, the number of items and the number of deleted items in the header is used in order to trigger garbage collection. Because normally when we delete entries, we just flag entries as deleted. But when we see that, like for example, 30% of entries are deleted, we can say like, okay, it's a good idea to rewrite this node in order to really remove the entries which are deleted. A very important thing about the IDs is that they have this time semantics. So basically, if you look at an ID of an entry in a stream, you can just already say if this what was the time in the local node in the moment this entry was added. And also, as I said, each stream item is a small hash instead of being a value. This is a contradiction compared to all the other things about Redis. For example, I don't know, lists, sets, whatever, is just each new element is a string. And if you want to structure it, you, for example, store like JSON or something inside the string. But if you think at it, for example, for the time series application, almost every user is going to need basically structured data. Every item will be, for example, sensor ID, temperature, humidity, and so you need these fields. Also, the fact that the stream semantically has the concept of fields means that it can do the fields compression. Otherwise, if they are just hidden from the point of view of the representation, you cannot compress them easily. So this is basically how I add an item in the stream. I use the xadd command with the key and whatever, and I use asterisk to say I want the automatic ID generation from the server, which is what you normally want. But instead, when you propagate the field, like in the append-only file or to the slaves, you do not use asterisk, but at this point, the master will write the ID that it's generated. And the reply of this command is basically an ID where the first part is the time, then there is a separator, and then there is a sequence number. The sequence number is important because if I add multiple items in the same millisecond, I want, of course, the IDs still to be different. And these IDs are guaranteed to be incremental. Even if the computer time jumps backward, they are still monotonically incremental, because what we do is to compare the computer time of the local node that received the write with the top item in the stream. If the top item is greater, we use the time of the top item in the stream and just increment the sequence number. However, since the sequence number is 64-bit, it means that basically we can add all the item in a stream in a single millisecond, because 64 bits is a very large counter. Sorry? What kind of encoding you use for the time? For the time, it's a millisecond Unix time. However, the IDs inside the list pack are delta compressed, because next items will have an ID which is very similar to the previous one. So it's a shame to waste 128 bits for every new ID. Instead, with delta compression, most of the times we just use 2 IDs to represent the difference between the IDs. And of course, on top of this, we implement like xrange, that given 2 IDs, or just 2 times in millisecond, can extract basically a range inside the stream. An interesting thing about this is that we don't need for streams like scan. You know, For scanning, for iterating the key space of Redis, we use scan. In order to iterate all the elements inside the set, we use sscan and so forth. For the Redis tree, for the stream, fortunately, we don't need that because we can just use xrange using special IDs. Minus ID means the minimum ID possible, and plus means the maximum ID possible. So I just start with xrange minus plus count 10, get the first 10 items. I get the last ID returned by the server, increment just a sequence by 1, and ask again for the next slice and so forth. And I can just run all the stream in fetching the number of items that I want for every iteration. This is an example of what I said, like xrange, my stream minus plus, and it returns like the first the 2 items. And as you can see, each different item has a different set of fields because every item is independent from the other. So what's the speed of range queries in streams? Basically, the complexity in theory is log n, because it's a radix tree, and of course plus m, which is the number of items which I return. So if you use a small count, like count 10, you can consider the time to be just logarithmic, because log n plus 10 is log n in big O notation. The time complexity is the same. However, if you try to fetch 50 millions of elements, of course, then the m becomes an important part. But if you think about it, because of the list pack, which represents many items, there is also a scanning part, so the constant times are high. Like I seek the right node, but the start ID of the range query was like in the middle of this macro node. I have to skip the first 50 items and then I can continue fetching them. So it's like not like certain other data structure where we can deliver like 200,000 queries per second or even more, but it is able to sustain 50,000 queries per second per core without any problem. So it's like sorted set range queries. You know that in sorted set you can get ranges by score. This is the same speed, but with 10% the memory usage of sorted sets. So it's a big win. And yes, the reason is because of this representation, you have to scan the macro nodes. So I said xrange is also an iterator. So far, what we basically outlined is just a plain Redis data structure. You have commands in order to add new things. You have range queries in order to fetch ranges and whatever you want. But what if you want to consume the items that are arriving in a stream in more complex ways, like blocking ways, or you want to be part of the consumer group or whatever? And so this is the second part of consuming the stream. The first command that I introduced after the basic commands is xread. Basically, xread is kind of like xrange, but you don't say like I want from here to here. You just state the last item that you obtained, and Redis will give you only the items which are higher than that. So basically it's a way in order to consume the stream part after part after part. And you have also count or whatever you want, and you have a block option for that, so that if there are no items, we satisfy the fact that the ID must be higher than the one that you communicated, it will block, and as soon as a new entry reaches the stream, it will unblock. Another very important thing about Xstream is that it supports multiple streams in the same call. So for example, let's return to the Slack chat example. Maybe you are a user and you are subscribed to multiple Slack channels, and in a single command, we want to check if there are any new messages in any of the chats we are joined right now. So it's very important that Xthread supports these semantics. Also, it's not like blocking lists where items are removed. Everything remains, of course, in the story. So this is how you use it, like Xthread block 5 seconds, count 10, and the streams that I want to listen for are keys 1 and keys 2, and I can say the ID, or I can use, instead of the ID, the special ID, which is $, which means just give me the new things arriving starting from now. I am not interested in the history, just from here to, and so basically, once Xthread will return new items, you take the ID of the last item returned, and you use again as an argument of the next call to Xthread. So basically what happens is that you have these streams, and different clients are at different places reading. And when they reach the end, they block, and new items are added, and they continue reading. So you have, in the history of streams, you have clients at different places. This is already nice, but unfortunately it's not enough, because what about this problem? Sometimes I don't want simply multiple clients consuming the same stream, but I want the same stream consumed in parts, different parts by multiple clients. Messaging is an obvious case. For example, you know, Kafka streaming with partitioning. Basically, this is an implementation of the same idea in completely different terms, but with the same goal as Cassandra. So I say, I have 3 clients and I want them just to have completely different messages. And there is a very strict rule here. There are to respect elements that are provided to a given consumer should never ever be provided to a different consumer. So this is a very important rule. And also a consumer should be able to access his own history. If he wants, or if it wants to see what's the history of the data items that was delivered to this client, the visibility should be basically blocked to the items that were really provided to it. And also, this should support recovering after failures, and should be easy to implement the client side, because maybe just on top of what we saw, you can implement that in your own client library, but it's complex. So, in order to implement all this, we have these new objects that are called consumer groups. Instead of clients directly pointing to the different part of the stream, we have this abstraction, which is a layer of access between the stream and the clients, which is a consumer group is a stateful object. It has the idea of the last ID that the consumer group provided to any client, and also for each client, it must remember a number of things. For each client, we need to remember what are the pending entries, what are the entries that we provided to this client. So how can the server have visibility of what item was provided to what consumer? The simplest way in order to model this is to have explicit acknowledges. So basically, when a consumer gets a message, when the message was really processed, the consumer should acknowledge the processing of the message to the server. In this way, basically, we can remove from the pending list of the Redis memory the item that was already consumed. And when the client will try to access the history of the pending entries, this acknowledged entry will no longer be there. So basically, the gist of this is that in the consumer group completely tracks who got what message and if this message was already processed or not. This is basically the API. So you create a consumer group. My stream is the key. My group is the name of the consumer group, and you have to to tell to X group create, you have to tell an ID, which is the first entry that will be provided in the consumer group. If we use dollar, again, it's like this consumer group will start consuming entries which are new and we are not interested in the history. If we use 0 instead, it means I want to consume this stream starting from the first message that there is this, or you can use whatever ID you want in the middle if you want. And then we have Xthread group, which is a version of Xthread which implements consumer groups. Like block 5 seconds, the group I want to consume from is my group, and I identify to the system as consumer 1, 2, 3. Because for this to work, every client must have a unique identifier. And so in every call, you tell the server who you are. Like I am consumer 1, 2, 3, I am consumer 5, 7, 8, and whatever. And I have then the list of streams, and I use a special ID which is greater than to say I want only messages that were never delivered to another consumer. So basically there are 4 special IDs in streams. Minus is the minimum possible ID. Plus is the maximum ID possible. Dollar means the current top item, and greater than that means the first ID which was never consumed by another consumer. So greater than that means just give me the new stuff that you didn't already provided to it. If instead with Xthread group you use, instead of greater than that, you use an actual ID, you access the history of the pending items that you still have pending. So you access your local history. Finally, when you consumed when you processed the entry that you received, you use exec in order to basically acknowledge the processing of the item. So it's important to understand that the way for the server to identify a given consumer is its name. So one of the things that still are part of the client duties is to come up for each different consumer with a different name. Okay, we told about this. This is okay, but there are still problems to solve. One is observability. One of the most terrible things in messaging system is that you don't know what's happening, like if clients are processing messages or not, who is behind what's happening in general. One important thing about consumer groups in Redis is that they are fair, which means the first to wait for message is the first served. And another thing which is very important is since it's not partitioned like Kafka in different partitions or like mapping to actual nodes, but it's just what you get is tracked. Different consumers can consume messages at different speeds, and the system will adapt to the different speeds that the different consumers have. However, there is another problem. Like I have these consumer groups, and I have different consumers reading from it, and then a given consumer crashes and never recovers again. But it could have pending messages. So what happens with the pending message? It will never be processed unless we implement some new feature in the streams in order to be able to recover these messages. Well, the feature that Redis Streams uses in order to fix this problem is message claiming. Basically, with X pending, any client can see in a given consumer group what are the pending messages. Messages that were already provided to some consumer, but we didn't show the exec acknowledge. And we have information about exactly what's happening because we have the idea of the message, we have the name of the consumer, which is this pending message, and we have also the idle time of the message, which is the last time, how many milliseconds elapsed since the last time that we provided this same message to some consumer. And we also have the number of attempts at delivering the same message, because usually what happens is that if a message is malformed, it could happen that consumers try to consume it and crash and crash and crash forever. So because we have a counter tracking the number of times a given message was basically delivered, we have like a dead letter feature. At some point we understand if there is a problem with a given message, and the system can like log those message or send an email to the system administrator or whatever it wants. So if a client sees that this message is pending for a lot of time, it can decide to claim the message. Claiming means that the given message changed ownership. The message was of consumer 123, and then instead it is claimed by the new consumer. And the way I use xClaim is also specifying the minimum number of milliseconds of idle time the message should have in order for the claim to be successful. This is useful because imagine that multiple consumers are checking the pending list in order to claim the messages. If multiple consumers at the same time try to claim the same message, we will have trivial multiple processing of the same message that can be avoided. In general, once a guaranteed single time processing is not possible, but at least in the trivial cases, we want to avoid double processing messages. So, because there is this minimum idle time, only the first claim will be able to claim the message, because the first claim will update the idle time of the message, and the second one will fail trying to do the same, okay? And finally, the message changed ownership and can be finally processed. All this was basically already implemented in Redis Unstable, the branch, and all these features will be part of Redis 5.0. The streams are very, very, very solid because I did something completely nuts in the unit test, like fuzzy testing, trying to make the allocator fail at different stages, and then checking for memory leaks automatically, or all the Radix tree which implements that is tested in an excellent way. So I believe it's stable. But from the point of view, instead of the higher level thing like the stream itself, the consumer groups, I feel like there is not still enough testing. So I am confident about releasing release candidate 1. But then I want to write new unit tests, more fuzzy testing, not at the Radix tree level, but at the API level. And after the release candidate 1, I also need the help from the community in order to test it better. And if we find that it's stable enough, we can say, okay, this can be general availability. Also, one thing which is very important for me is to document this very well before it's released. You know, it's terrible to release new code like a stable, but there is no documentation for it. And I'm writing like a very long document, which is like a tutorial about using streams in Redis, which is nice because, as you can see, it's a bit more challenging to compare to the other Redis data structures. There are many commands. The semantics is a bit, peculiar, but we are almost there. Okay, I think I ran out of time, so thank you for attending. Thanks. Sure. If there is.
I'm Madhu. Thank you for sharing the knowledge. One question, is there any partitioning on the data that you are actually storing? Like you haven't touched upon, like, the consumer group, when you enter into the stream, basically, is there any way to partition the data? Like, let's suppose that you have like more consumers to the group. Now you add, is the data going, like one particular set of data going to the one consumer?
So in general, the stream itself, you cannot partition like in the multiple nodes because it's a single key and follows the normal semantics of Redis. But a single stream can have as much consumer groups as you want. And basically, each consumer group can have as much consumers as you want. Is that that answers the question?
So I was wondering, like, how is the data partitioned, basically, like the Kafka? You say that here is a.
Oh, okay. There is no partitioning. It's completely a higher level. Basically, what we do is the current set of messages which are pending are completely in the memory of the server, all the IDs. So basically, instead, if you partition like in Kafka, the problem that you have is that if in two partitions, you can have a client which is very powerful, and can process a lot of messages, and in other partition a slow client. Instead, what we do is just a client arrives and asks for new message, and we provide it with new messages, and we remember all the IDs. So without any partition, we still can be sure that we will not provide the same messages again to a different client. Because then the messages will be acknowledged, and the minimum ID provided, the maximum ID provided, will be stored in the consumer group, and we will provide only new messages. So basically, the partitioning is logical. It's not really using a partitioning rule.
Okay, thank you.
You're welcome.
Hey, just a couple of questions. I have more for. So, how is the radix tree built? Is it based on the string representation of a timestamp?
The radix tree?
Radix tree, yeah.
Radix tree, basically, the key is the first ID of the first entry inside the list pack.
Okay.
So basically what you do, because the radix tree implementation I wrote has seeking capabilities where you can see, for example, seek the item which is greater or equal to that string.
Yep.
So basically just you seek the first node that could contain this entry, and then you scan.
Yeah, okay. Second question is there any facility to automatically rotate out old items in a stream?
Yes. You have two systems. One is the XAdd maxlen option, which will trim the stream as new items are added to the maximum length you specify. You can specify both precise trimming or fuzzy trimming, and which is much more efficient. It will not guarantee like to take your number, but will remove wall nodes, which is much more efficient. The other one is an xtrim command, which can be used to remove ranges from the old part of the stream. In this way, you basically can use xrange and xtrim in order to fetch data, move it, for example, on disk, and remove from the server.
Thank you.
You are welcome.
Hey, hi. Thanks for the insight into the streams. How does streams work with high availability? Like, will I be able to consume streams from slaves?
That's a good question. One of the reasons why there is an xread command and an xread group command is because the first is a read-only command, but the second one is a write command, because xread group, as a side effect, changes the consumer group. Now, one important thing to visualize is that the consumer group is part of the data and is replicated, saved in RDB files and in an AOF file. So, like if your instance restarts, all the state of the consumer group will be the same. No, nothing is lost. So basically, xread group you cannot send to the slave, but xread you can send. So if you have a lot of consumers that are consuming the whole stream, you can use slaves in order to scale your workload. But instead, if you want to use consumer groups in order to have a partitioning of the stream, you cannot use slaves, and you have to send this to the replicas, to master. With range operation, like in time series applications, xrange is a read-only command, so you can use slaves. So the only consuming option which is not available for slaves is xread groups.
Yeah, question here. Is the list pack format specific to Redis, or can it be used as a generic representation? Like, can it be used outside as a standalone component for representing data of that form, or is it specific to Redis?
That's a very nice question, because actually I went to full efforts in order to make sure that this was not just trapped in the Redis. It's built as a completely different library without any hook inside the Redis internals, and has also a specification document that states exactly how the encoding works. So basically, it's BSD license. You can just take listpack.c and h, copy it in your project, read the specification, and you can use it in anything.
That's really nice.
Thanks.
Thank you all. Lunch is served.
Thanks.